Welcome to class 49 of CS2. We'll talk about the possible causes of non-stationarity. We have mentioned three here. It's not that these are only the three causes of non-stationarity. There are other causes as well. So the list I've written here, that is not exhaustive. Even the list whatever I've written here 1 to 3, they are not mutually exclusive as well, because there might be a combination. Whenever you see non-stationarity, maybe you have two kind of things combined together and your data is non-stationary. Remember, whenever you want to apply time series model, the main time series model, there we use, whenever you apply time series model, make it sure that the time series is stationary. If the time series is not stationary, then you cannot apply the main Box-Jenkins method. Okay, so to apply that, make it sure that the time series is stationary. So if directly you get a stationary time series, which is rare in practice, then you can apply the method and find that. You will see in practice the main three types of non-stationarity. If you remember, we have discussed about integrated process before, so we talked about this all the time. You can write in the form of a arima. You can write in the form of a arima if the time series is not stationary but it's integrated. Finally, what will happen? You apply differencing twice or thrice or whatever number of times and see that it's stationary. Okay, sometimes what you see, you will mark one AR2. If you look, it will look like AR2, even it's AR2, but non-stationarity AR2, it's non-stationary. Okay, or maybe ARMA 23, ARMA 21, whatever, you will see directly this is non-stationary. But if you transfer this one, it will take ARIMA form. But not all non-stationary AR2 or ARMA 21, they will take ARIMA form. Okay, ultimately when you are differencing, you are taking out the unit roots, nothing else. Okay, you are taking out the unit roots. So if there is these are non-stationary due to the unit roots. Suppose you have 1/2 if you apply differencing, then this will vanish. If even you have two ones, these will vanish. How about these two? Again, it's non-stationary, right? So what will happen? You can never make it stationary by regular differencing. That's not possible. There must be some other problem. If you have 1, 1, 2, 3, then that's fine. If you apply differencing twice, then you will have two roots and that will become stationary. This is only one form. You will be able to know whether you can transfer it to stationary or not by using this one. So we discussed part 3 already, ARIMA, but there might be other forms. So we'll see one deterministic trend. It could be linear or exponential or any kind of deterministic trend. Okay, mostly we see one of these kinds. There might be a combination of factors as well. Then we'll see the seasonal effect. How can you transfer to stationarity one by one? Let's start with the first one. We'll discuss 1 and 2 today. So when we say linear trend, suppose you get data in this form, time 4, we know the values. Okay, so suppose you want to predict for December. Okay, December is 5. Now in December you want to know this figure here. We have data up to November. Okay, this is August. This is 1st of August, this is 1st of September, this is 1st of October, this is 1st of November, and you want to know the value on 1st of December. Okay, the gap is 1 month here. So this is our time series 3.01, 4.992, 7.011, 8.993. This is not stationary. We are sure that the data we see is non-stationary because there is a clear indication that it's increasing. There is a trend here. Okay, so how can you remove the trend? We say trend removal. Okay, so if you want to remove the trend, the linear trend we see, you must establish relation. Remember in CS1 we must have studied this way, the variables x and y, but the variables are t and xt here, the time, you write time here, and value of the stochastic process here. So we have t and xt now. This is time series and this is time. If you compare with linear regression, whatever we studied, we had bivariate data. We wrote this way 1, 2, 3, 4 or whatever. Not necessarily 1, 2, 3, 4. Here time, that's why we write 1, 2, 3, 4. Two variables. You can say height, weight. Okay, 160, 40, 165, 48. This way you can write. So we wanted to establish relation between x and y using a linear relation, right? Y is equal to a plus bx, suppose y is equal to a plus bx plus some kind of error. This was the formula. I mean, if you write it properly, it is like yt, okay, yt is equal to a plus bx plus et, that way. The error at time t, we write that way, okay, suppose this way. But remember, the data we had x1, y1, x2, y2, x3, y3, that way. But here t and xt, time and the value, because we are talking about a stochastic process. We are not talking about two random variables. We have so many random variables here, x1, x2, x3, x4, x5, that way. And in case of a stochastic process, you get one sample for one random variable. One sample for one random variable. Remember, here we have only two random variables. X, when you say, we get a lot, x1, x2, xn, y, y1, y2, yn, but yeah, the analogy that is similar, okay. So now here you need to predict this one. So how to predict? We want to apply a time series model here, AR1, MA1 or simple ARMA11, okay. You see, in 90% of the cases we take ARMA21, ARMA11 or AR3, AR2, MA2, that way. Not very complicated models. Anyway, I am not going to that. There is a criteria, we will discuss that separately. Coming back to this one, we have this time series data, and if you know that there is a linear trend, if you want to remove the trend means here technically you don't consider the trend thing here, okay. What you can always predict from now, you don't need a time series model for that. Even if you apply forcible time series model, it will not work. See, what we can do is, I will write this way, this is 3.01, okay. So 2x plus 1 formula, 1 plus 2x, 1 plus 2 multiplied by 1 plus 0.01, and this one is 1 plus 2 multiplied by 2 plus minus 0.08, and this one will be 1 plus 2 multiplied by 3, okay. 3 is the time, 2 is the time here, 1 is the time, plus 0.011, and this one is 1 plus 2 multiplied by 4 plus minus 0.993, this is 992, so 0.07. So when you predict here, what you want is, you want to take the time series, this one, okay. This is our time series, 0.01 minus 0.08 plus 0.011. Remember, I must have discussed yesterday these kind of time series. One is around mean. When you write xt, there will be no mu here, mu is 0, then you will get this way time series, it will revolve around 0, okay. Now we can have this time series like this with mu 2, then what will happen if mu is 2, then around 2, this is the time series, okay. So what is mean here? We get a zero mean. Okay, zero mean time series. If you want, you can include one here. Mean will be one, but not necessary, because whatever things you know by now, okay, that for that will not apply any time series. See what we want to do. Removal means what? We removed this from the time series data. We removed this means what? Will not use in our time series data. We'll apply a time series model here. Suppose I want to apply AR1, ARMA11, whatever. I will apply a time series model here to this data to predict this one. And then what I will do, I will write that value here plus. So this one, the prediction, the time series model I will apply here. Okay. So for linear trend, we write xt is equal to a plus bt. See, there is no x here because the independent variable we say, that is t and xt. It's like y and x, plus we write et, white noise process. Here you can write yt or et, whatever. Remember, this is a zero mean white noise. This is stationary. So this is stationary data. You apply your time series model, you try to predict this one. Suppose I got 0.03. okay, I will write here, after applying a time series model here, I will get this one. I removed the trend here, okay, and then I will write this part separately, 1 plus 2 multiplied by 5, because this is time. Okay, there is a time dependent thing, that is 1 plus 2 multiplied by 5. Here 1 plus 2 multiplied by 4, here 1 plus 2 multiplied by 3, here 1 plus 2 multiplied by 1. So this one I will write separately. Removal means what? I am not removing. Removal means while applying time series, I didn't consider this part. So ultimately you get your prediction, but not directly only on this data. Okay, this is a white mean. So here this is our original time series data, where we thought, or we observed the linear trend, and we try to apply this where yt is zero mean white noise, which is stationary, and we'll apply a stationary model. Zero mean stationary model, the type 2 use normally. So where mu is not there, and we'll try to predict this one, and then we'll put here, we'll get our prediction. Okay, so this is one of the ways we can remove the trend. Okay, this one we studied already. Now cycles must be there. How to manage the cycles? Even before going to cycles, there is something. How can you find, how can you write, how can you establish relation between the time points and the values? Okay, for that we can use linear regression. Okay, this is linear regression formula. So linear regression, when we say, it's like a plus bx, ab you need to find. In my case, without estimating, I wrote the data in such a way that my a is 1 and my b is 1 plus 2t, right? A is 1 and b 2. Without estimating, I wrote 1 plus 2t, because I wrote the data in this way. Even for this data, if you apply, if you take this as x and you use actuarial table, or you use the formula to find alpha and beta, a and b here, okay, using the formula there in your material, you will not get exactly 1, 2. Maybe you will get 0.98, 1.01, and 2, I have 1.98 or 99. You might get this way. You will not get exactly 0, 1, because according to me, whatever is the random shock or white noise you say, that might not be the case. Okay, you will get some a and b, but I wrote in such a way that even if you take these numbers, what I want to say is, if you take this way, the line we're talking about 1 plus 2t, that might not be the line of best fit. This is a line of fit, I agree. This is a line of fit. Okay, for this data, whatever four data points I've taken, this is one line of fit I've taken randomly just to explain you. But if you want to find the line of best fit, okay, in the sense the sum of square errors is minimum, that way what will happen, this line will represent the data properly, I mean as compared to what I have taken. But just to explain this one, I said this one, you apply linear regression and you can estimate the parameters, okay, and you take this one that way. So the same method we will use, regression method, okay. The points we have xy pair here, txt pair you can use. We have a strict formula like x1 y1 x2 x3 x4 y1 y2 y3 y4. Using those you find AB, put here, and according to that you keep it separate. That is called removal here. You keep it separate, don't include in your time series forecasting, okay, and apply here, and finally you add and you get your value. That's all. Now let me go to the seasonal one, okay. Again there is a concept of odd and even will come. Sometimes it will be odd, sometimes it will be even. So if there is a periodic variation, or maybe seasonal thing, how can you manage? So periods also, it might be odd or even. Let me write one odd, one even. Suppose I will consider 4-month period, okay. Suppose I will consider 4-month period. That means after every 4 months the things repeat, okay. They will be almost equal. If you consider a particular thing, winter sales, okay, they say, so that kind of a discount, or Black Friday, so that kind of discount that comes every year, okay. So that is yearly data. So something which repeats in every 4 months, suppose I will write this way. It's not exactly like 10, 20, 30, but yeah, let me write 10, 20, 30, okay. 4 months, 4 into 3, 12, then 10, 20, 30, 10, 20, 30. That way you get. So there is it's deterministic, right? So we can say that they are random, okay. There is a past dependency all the time, and it's kind of the same thing comes once again, time and again. So it's a 4-month period data. So the real data will not be like this, okay. The real data will be like 10.21, 19.91 or 97, that way, okay. So I've written this way. In that case, what you can do is, you can see the periodic variation, okay. You can apply simple linear filter here. This is called method of moving averages. You find the average of these three. You find the average of these three. That will be 20. Then find the average of these three, okay. 20 plus 30, 50 plus 10, 60 divided by 3, 20. Then take the average of these three. Moving average, right? 30 plus 10, 40 plus 20, 60. 60 divided by 3, 20. See, it becomes stationary. And take the average of these three. That is again 20. So in reality, you will not get 20, 20, 20, 20. If you get this way, then you need not apply any time series model. Suppose the data is exactly this way, then you don't need to apply any time series model. You predict 20 for next time, okay. Then of course we have to get back to this one. We want to predict here. It will not be exactly 20, 20, 20, but maybe it's around 20, 20.79, 19.32, that way you will get, okay. So that will be around 20, and you can take mu 20, your mu is 20, plus other things you can get, okay. This is not a zero mean, but yeah, you have a proper time series. You will get a time series if you take the real data, and there is a 4-month seasonal effect, okay. I mean the period is 4 months, so there is a periodic variation, I can say. Then you will, this data is this data is stationary, and you can apply, you can predict this part. Again I am saying, if exactly you get 20, 20, 20, in mathematics we write we can never get the data the way we want. Okay, this is real world data. Then you will predict this one. Okay, then from here again you have to go to this to predict the final one. So the formula for that is yt is equal to 1 upon 3, very easy, xt minus 1 plus xt plus xt plus 1. If you apply this, okay, suppose we know this 10, okay, 10, 20, 30, and if you start writing x1, x2, x3, x4, x5, x6, x7, x8, x9, and you want to know x10. Now here we'll write x1 plus x2 plus x3, 1 upon 3, that is our y2, actually it's y2. Okay, so this is my y2, this is my y3, this is my y4, this is my y5, and this 20 I got, if you see, because I've started from y2 here, when x2 I have y2, and this one I don't know, I want to know this one. Okay, y10 I want to know, so I want to know y10. This is my question. Okay, so y10 will be equal to 1 upon 3 y9 y10 y11. Okay, yes, I know x10, y9, sorry, let me write x10, y10 is x10, x9, x10, x11. Okay, so I wanted to predict x10, actually I wanted to predict x10, I don't have x10. Okay, so 9, 10, 11 I have to take. If I take 8, 9, 10, okay, 8, 9, 10 I will take, better, let me write 8, 9, 10. 8, 9, 10. Okay, that will be y9. So this must be y9, this must be y9, this must be y8. Okay, this is y8, this data up to this we have, let me write this 20, it will not be exactly 20, it will be around 20, this will be my y8, you can verify that, and I will predict y9 here, I will predict y9 here using the data up to y8, because I have up to x9, I don't have x10, I want x10. Okay, so what I will do is I transform this way, this is called linear filter, I transform the data this way by taking the moving averages, and I got y2 to y8. Okay, I don't have y9, I want to get y9. So if you apply a time series model, you will get y9. Okay, because this is stationary, you can apply time series model, you will get y9. Now put y9 here, we have already x8 and x9, you put here, there from there you will get x10, and this will be your answer. Okay, that is how you have to manage. Now if you have a 3-month period, odd 3-month period, then the formula is a bit different. Okay, the formula for yt will be equal to, you can think on this, 1 upon 4, you write half this side, let me write xt minus 2 here, and plus 1 upon 2 xt plus 2. Okay, that is xt minus 2 x plus t plus 2, and the 3 in between I will write xt minus 1 xt plus 1. Okay, this way you have to take. I took this one, actually 1 upon 3 this for even. If you take the odd month, 3 month, then you have to write 1 upon 4, here you take half, here you take half, and these 3 anyway they will be there. If you see the formula, here, this formula if you compare, okay, for a even month, 4-month period, so that there will be 3. We are talking in a year, okay? Year is constant. How many times it repeats in a year? If it repeats 4 times, then you have to take this formula. If it repeats 3 months, you can apply this formula. Then you can take for other periods like 6 months or whatever comes within a year, you can take that, okay, accordingly. So remember, only even and odd will you need to see. Even or odd. Even means directly you will get this way. Odd means you will get this way. You get half both the sides. If you can come up with any other formula that will work, that's fine. Okay, that's up to you, but you can verify this one. Then the next one is seasonal differencing. Okay, seasonal. That means the data repeats, though these days we don't have that much craze in greeting cards, all that, but yeah, 20 years before or maybe 25 years before, we didn't have internet connection and online stuff, so we used to buy physically, okay, the greetings card sale. The same example is appearing time and again here also. Suppose you want to know the sales figure, and during 1 to 5 January, okay, if you see around 1 January each year, suppose you know the data for 2000, 2001 and 2021, okay, and here this is not one monthly sales figure, 1 February 2000, that way you know up to 1 December 2021. So 12 months you can multiply with 21. You have a lot monthly data, sales figures, okay. So you can start with 1, 2, that way. So you know up to this, and you want to predict for 1st January 2022. Sorry, this is 1st November, okay. And you want to predict, or maybe you can say 31st November, 30 November, and here you can consider roughly monthly, okay. And suppose we are in December and we have data up to this. Let me continue with the same example. 1st December. So monthly data, we have all this monthly data, and we need to predict for 1st January 2022, okay. So if you take all monthly data, it will not be useful, because what happens is here only once in 12 data, only once you have something that you need to consider. Otherwise, if you consider all, you can say all useless stuff. I mean, when we talk about the sales figure of greeting cards, okay, so if you have this data, small data, they are not contributing at all, okay, these are the data which are really not contributing, and again you have a very high peak here around January. So if you know that January matter, like in Delhi now, the air pollution, if you see the air quality index, that's very bad, okay. So when it's very bad, it happens every time nearing Diwali, right? From that day it starts. So there are thousands of reasons maybe, but we are, as ordinary humans, we are unable to manage it, and we always create records, and India, particularly Delhi, becomes number one. So you must have 1,000 reasons, but yeah, we are unable to do that because we have so many population and all that. I mean, that way the things appear time and again. So if you want to do something for that, you should not consider all March, April, May and all that. Most of the time it's just above normal, and that's fine. Like Indian cities, if you consider, and not India, UK was like that before 40, 50 years maybe, or maybe 70 years. UK was like that. Around 1960, you must have heard the smog, and so many people died. But yeah, this time, because due to industrialization, it's happening in India. Maybe after 20, 30 years, everything will be fine. What I'm saying is, when you know that things appear this way, why to consider all data and make it problematic? So if you apply a time series model here, it's not stationary at all. There is a very high number in between and these numbers are here. This is not stationary. So what you can do is, how can you predict using only data like this? For that, will not differentiate this way. If you apply differentiating this way, then that will not work. Okay. Here our data, new data, you can write yt is equal to, suppose our new data is yt, we write delta 12 xt. Delta 12, how I write? xt or xt? Okay, let me write xt. This is yt. xt, I have written capital xt, that is yt. Okay, that is actually xt minus 12. xt minus xt minus 12. Okay, that one will be, if you put whatever values you have, suppose you start writing here x1, x2, x3, x4, x5, that way, x12, x24, that way. So we want xt minus 12. Okay, so this with 12, delta 12 here, you will be able to get the data which will look like the same. Okay, and then you can apply time series model to forecast. So where we can apply time series model, if there is a time series which looks like consistent, you can say, okay, something which should revolve around particular point, there only we can apply. It's not that I covered everything. If you see, you might find something more, but yeah, we should not spend more than this much of time, not only when I teach you, but also when you prepare for the exam. Maybe it's a very rare chance that you will get a 3-mark question. So if you consider the exams before 2015 or 2019, so they used to ask a theoretical question from time series 2. You describe all these methods, 5 3-mark question. But nowadays, because we have a whole lot of things, they come up, they added so many new chapters, 3-4 new chapters. Okay, it's huge, and also we have R coding. So I don't think this is that much of importance. Only for knowing purpose I explained you, because this is a part of the course. So we'll move forward and we'll do one problem. We'll see how can you apply Box-Jenkins method to predict. And in the next class, I will discuss more about partial autocorrelation, taking time series data. How can you estimate? Even in this class also we'll do one. Okay, one problem anyway we need to do. Let me write here bit of estimation. Now I can write one example here and we'll see how to estimate. You must have studied estimation in CS1. Okay, similar kind of estimation we'll do for time series as well. So when we talk about estimation, you need to estimate. Okay, suppose you have data. Let me write data here. Data x1, x2, x3, xn. Data, when I say this is past, we already know we are here and we want to predict the value here. We want to predict here. So when you consider the time series in totality, then if you take the average here, okay, if you take the average here, the whole average, okay, that will give you mu. Mu is the average of the stochastic process. Suppose the random variable here is x1. Now this now because you are here, this became known now. Okay, this also, these are the realizations, you can say. We know all this. Okay, these are no more random variables. This is now random variable because we want to predict. And even I can write this way. When I predict, I am here. Okay, I have data up to this. this prediction will be this. I don't have this data. Okay, the prediction here, that the notation we'll use here is xn. Okay, because we know up to this data we are here. You can, although we are here, you can think that you are here. Okay, we know, and will predict for this one, and this is the prediction. I mean, this is the original data. We'll be able to know at time n plus 1. Suppose 1st January 2022, this is 1st January 2021. So this is the prediction. Now on 1st January 2021 or any time in between, when we have all this data, we can predict for this one. That is called one step ahead forecast. One step ahead forecast. If you predict for this random variable, we don't have this data, that will come later after another year, but you can predict staying here. You can predict with up to this data you have. That the notation for that is xn1, xn2, 1. That means up to n we know, and we should check that they are close. Okay, because we predicted. We'll predict this way. Okay, we'll have a confidence interval kind of a prediction. I will show you in the graph. Also point estimation. But before predicting that, you have to apply a time series model. Before applying time series model, make it sure that the model you get, the data you get, you can apply a time series model there. If you can't apply using all these procedures we know, we'll try to transfer to stationary, will apply and will predict. Okay, the general method is there. We'll do one problem. But before going to that, you need to estimate the parameters. Okay, so how can you estimate mu? Because mu is the mean of the process. Whatever data we have, we'll estimate mu from that. Okay, so simple average will take mu cap, that is estimation of mu, that will be summation xt. You can write 1 upon n xt, t is 1 to n. That way you can estimate mu, and you need to estimate the autocorrelations. Okay, we write here cap. Okay, cap means these are auto covariances, then we'll have auto correlations. Okay, so auto correlations we write rk here. Rk are this cap divided by gamma naught. Okay, these are rk. These are the sample autocorrelation. Remember population autocorrelation, rho k. We'll discuss more about autocorrelation, partial autocorrelation next time, rho k and phi k. But these are the sample autocorrelation. Rk sample autocorrelation. Remember in CS1 we had concept of R and rho. R is correlation between two variables x and y. Rho is population correlation. This is sample correlation. Okay, suppose you consider all actual students and you record their heights and weights, and you see the association between their heights and weights. Okay, suppose you collected 100 data, then you get R from here, because this is sample. But if you want to rho for them, you don't know rho. How can you know rho? Rho is a population one, population correlation. There must be a formula only. You can only estimate rho like you estimate mu. So to estimate this one, we take the help of a confidence interval or point estimation, or you can test a hypothesis for rho. Exact rho you don't know. Okay, so rho is something which can be estimated from the data. R is exact. R is sample kind of a thing. Similar to that, we have this one. This one will estimate from the data. You will never get this from the data. Okay, this can only be estimated, and this will be equal to Rk. Rk is partial. If you want to compare, you compare with this one. This is our population autocovariance. This is sample autocovariance. From sample autocovariance, you can find sample autocorrelation. This is population autocorrelation. So the estimation of this will be this, because you have formulas for this. Okay, to find rho k and all that. we can't use formulas. Okay, we'll have data, we have to predict. From data you can estimate. Okay, so how can you estimate auto covariance? If you know covariance, auto covariance like covariance. If you know how to find covariance, if you get bivariate data, if you can find covariance, you can find auto covariance. Okay, it's similar. There is a little bit difference. I'll write here, you will be able to understand. If I write gamma 1 or gamma 2, will be able to follow. Let me write the formula for gamma k cap. Okay, that is 1 upon n summation xt minus mu cap, and then xt minus k minus mu cap. Okay, so considering that you know mu, you can write this one will be from k plus 1 to n. This is the formula. T is the variable here. If you want, you can write t also here. Okay, that means if I want in a tabular form, let me write the time series xt here. Let me write the time series xt values here this way. x1, x2, x3, x4, x5. I will write xt minus 1 here. That means this will be x0, then comes x1, then comes x2. So I am interested in the t minus 1 values. Okay, so let me write here. Here also I can start, if I want, I can start from, if t, suppose I want to know, if you put 0 here, okay, k plus 1 will be, t will be from k plus 1. It will start from 1 anyway. Okay, so it's okay, we'll see that. Suppose I want to find this one. Okay, you put k1 here. K1 means you will get from 2. So 1 upon n you fix here. Suppose n is 10, summation. If you put 1 here, I'm not going to 0. Okay, we'll go to 0 later. If you put k1 here, so t will be from 2 to 10. Okay, t will be from 2 to 10, xt minus whatever you must have got mu cap before, that is the mean, and then you have to write xt minus k here. T minus k we have taken here 1. Okay, so t minus 1 you have to write minus mu cap means x bar you can say here. So we'll find the average here, average of all this. Suppose this is mu cap or x bar, I can write mu cap, you write. Okay, or if you want, you can write x bar also. You just find the average of all this. Similarly, this side, in place of writing x and y, normally we used to write x and y. We wrote this way, if you remember, x1, x2, xn, y1, y2, yn, here x bar, here y bar, x1 minus x bar, this minus this bar, sorry, this multiplied by this, x1 minus x bar multiplied by y1 minus y bar, x2 minus x bar multiplied by y2 minus y bar, xn minus x bar multiplied by yn minus y bar. This summation we used to find, okay, before dividing by some number. So similar to this, the only difference is when we say auto covariance, when we said covariance between two random variables x and y, we consider two random variables x and y. Here, because this is a train, we don't have different buses here. Two components of the train, they may be next to each other, or maybe sometimes we'll consider this way. Okay, the correlation between these two. Okay, the correlation between this and this, and then this and this, 2 that will give you gamma 2. This will give you gamma 1 cap. What is the difference? Suppose you want to check the temperature between January, February, March, April, May. Okay, this will give you gamma 1. If you want to check the temperature between January, March, May, July, September, November, 2 months. Okay, so monthly data you have, but you are finding gamma 2. Auto covariance. See, we have one stochastic process, but we have so many random variables. We can check with 1 month gap, that will give you gamma 1. If you find with 2 month gap, you will get gamma 2. If you find with 6 months gap, you will find gamma 6. If you find with 12-month gap, okay, every January, then you will get gamma 12. So all kind of auto variances you have here. But if you have two random variables, we have only one covariance. We say gamma, that's all. Rho, okay, we say this way. Covariance, here auto covariance, here two random variables, here so many random variables. Okay, here there is no kind of a lag concept. Okay, directly you have two random variables, you find how there is a link between these two, that we find. But here you can find this autocorrelation will come from autocovariance, right? They're linked. So when you find autocovariance, you can take 1 leg, 2 leg, okay, 6 months leg. This kind of an example is there. If you see the temperature in successive month, okay, you see the data. So after every 12 months they will match, okay. So this is the autocovariance graph. What will happen is it will increase, and see they are matching here, okay, here and here they are matching. It's like a cyclic graph. You know already the sine graph and all that. I'm not going to that, but remember this way we have to find here. So I've written only for gamma 1 cap. So with one lag, what is the link we want to know, okay. So we apply this formula. Now if you apply this formula, if you start t from 2, so what we want to find, x2 minus x bar or mu cap. So x2 minus x bar, let me write here x2 if I want to write, this should be my xt minus 1, okay. So yeah, then x2 I will get, okay. So let me write x2 here, xt minus 1, so that will be x0, this will be x1, okay, this will be x2, this will be x3, this will be x4. I'm writing this way so that it will be easier for me, okay. So now I'll find this difference. Sorry, I will ignore the first one here. Okay, one data I have to ignore. That is the difference. When you consider random variables, we take all data. Here we will not take all data. So x2 minus mu bar, okay. So here x1 minus mu bar. So multiply this multiplied by this. It's similar to covariance, okay. If you consider two random variables, you go through the formula for CS1. It's exactly same actually. The only thing is, in time series data we get data only once. We don't have two data, okay, because these two match, they will match. We don't have two series of data. So we find this way, this minus this, 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 this minus this. You multiply a1 b1 plus a2 b2 plus a3 b3 a4 b4. You multiply everything, divide by 1 upon 10, divide by 10, or you multiply by 1 upon 10, 1 upon n, okay. I've taken up to 10 data. So you will get gamma 1. If you want to get gamma 2 cap, then you don't consider this one as well, okay. Now you have to find differences this way. Here x3 minus mu, then x1 minus mu, the difference is 2, okay. So here in place of t minus 1, see k comes here, so I'll write 2, xt minus 2. That means I will ignore x1 x2, x3 minus mu, x1 minus mu, plus x4 minus mu multiplied by x2 minus mu, x5 minus mu multiplied by x3 minus mu. That way if I find, that means if you see the train here, okay, you are seeing the link between this one and this one, then this one and this one, okay, this one and this one, two different autocovariance, okay, and this one with this one, that way. That is what we want to know. What is the link? Like I said, the temperature, if you see January, March, still there is some link. January, April, there is no link at all. January is the winter in India, and April is almost summer, okay, summer in most of the parts. So there is no link, the link disappears. If you see January, April, August and all, that way 3 months if you take, that is not same as taking one month. January, February if you take, there is still a great connection. So all these you can find in case of all these autocovariances. From autocovariances you can find autocorrelations, but these will be simple estimated autocorrelations, and even these only will get, we can estimate only, okay, the properties you get in population autocorrelations. So you have to estimate all this mu and this one, okay. Then we'll do a simple problem before going to the problem I've written. Let me write one example. So this example will complete, it will not take more than 5 minutes. Then we'll decide whether to continue or not. Maybe we'll not continue. That problem I'm bringing from last class, but I'm unable to do. Okay. So no problem. We'll do that next time. But one simpler example I will do so that you will have practical idea. Suppose you consider one MA1 process. Consider MA1 process. Xt is equal to Et plus beta Et minus 1. I can write Et follows 0 sigma square. And given the values, if you estimate this will be 1 anyway, because you will be seeing the relation between January temperature, February, March, that way, okay. And if you need to estimate this one, here this is given, this is a problem, okay. It's very easy, mathematically you can estimate, nothing to learn, like whatever formula I've given you, that formula you can use and you can estimate this one. Here it's given, maybe you have 100, 500 data, it will take 1 hour for you. So they've estimated and they've given you, and this is a problem. So now the question is, estimate parameter beta. See, there are two kinds of estimation given. I'll tell you the simplest one. Estimate the parameter beta. And if you are not working in a company and you are not working with time series model, this will be fine for the exam, this much, okay. So why you need to estimate parameter beta? Because ultimately what you do, you have to predict for future. When you predict for future, you will be needing beta. So we'll ignore this in Box-Jenkins methodology, okay. We'll not consider the future error. So if you want to predict for 11, okay, we have up to 10, x1 to x10, you are predicting for 11, then this error will take 0. It's similar to regression. So we'll not worry about this. But this, you know, you must get by that time Et minus 1. So there is one parameter beta. If you estimate beta, then only you can use MA1 model within bracket, considering that it's already stationary. You made it stationary otherwise by different procedures. There are online tools also. If you put any data, they will transfer it to stationary, okay. So now the only important thing for you is to estimate beta. How can you estimate beta from the sample? Or the sample estimated values in this example, they're the same, okay, because if you have sample, you can estimate. Now let me write gamma naught here, gamma 1 here. These are the sample one, covariance of xt, sorry, these are the population one, xt minus, sorry, here xt minus 1, xt, you write this one, okay. You know how to find this. I am not going in details, but let me write one line anyway. Beta Et minus 1 plus Et beta Et minus 1. We have already done for MA1, and you will get 1 plus beta square here. And if you find covariance xt minus 1, you will get beta, if you remember. If you get beta. So if you find rho 1 here, that will be gamma 1 by gamma naught. that will be beta upon 1 plus beta square. This is population autocorrelation. This is population autocorrelation, but sample autocorrelation is given. So in point estimation, you must have studied in CS1. In point estimation, we take sample mean is population mean, sample variance is population variance. If there are two parameters to estimate, if you have only one parameter to estimate, you can equate the sample autocorrelation to population autocorrelation. Okay, this is point estimation. So in point estimation, you equate the sample autocorrelation to population autocorrelation. Okay, so the sample autocorrelation we got minus 0.25. if you take rho 1 is this, then beta divided by 1 plus beta square will be equal to minus 0.25. You solve this quadratic equation, you will get beta will be minus 0.268, or it will be minus 3.732. okay, these are the values, you can check it, you will get. So once you get beta, of course you can choose the beta you want, whatever you want. Maybe you will get multiple betas, sometimes one beta. You might reject considering that the process will not be stationary. These are the things you can consider. Okay, so according to that, you choose one beta where the process will be stationary. Suppose I will choose this beta, it's a beta more less than 1. This is stationary anyway. We're considering MA1 process. I'm talking about normal ARMA process. Okay, so in ARMA process only you can apply. If it's stationary, you can apply a time series model. So in MA process is always stationary. Maybe you will reject this one, saying that if you take this one, it will not be invertible, though that is a lesser constraint. We are talking about stationarity. You consider only one which is not invertible. This is less than 1, beta more less than 1. See, we didn't find the solution of the characteristics equation. Okay, we are seeing the coefficient because it's only 1. If this is less than 1, this will become invertible. This is stationary anyway, or MA processor always stationary. Will not worry about stationarity. Once you know beta in MA1 process, you will be able to forecast for future. Okay, put beta here. This value you will get because you have the data. You put here and you take this 0 and predict this one. Now, if you want to do a general problem, it will look this way. We'll do it next time. Write down the defining equation for ARMA 1-1 process, and like see here, suppose an individual is fitted the following model to a data set. Okay, xt is equal to this one, ARMA 1-1. We're talking about ARMA 1-1. The most recently observed value in the series is x25. Okay, that means up to 25 we know. With estimated residual, see this residual is estimated from the data. If the whole data is given, you can estimate whatever way you want. Okay, now that you don't have data, they've given this one and this one, and you find 1 step ahead forecast, 2 step ahead forecast. So this one is actually x26. If you put x26 here, you will get this one. The original x26 you don't know. Okay, you are estimating at 25. You are at 25. You want to predict for 26 and 27. These are the notations. 26 and 27. You have to predict for these 2 points. You are here. Okay, you are here. So up to 25 you know. So if you put 26 and 27 here, you will get the values. Let me put 26. I know already this is mu estimated from the data. You need not do anything. This is estimated. Okay, we say alpha 1 xt minus 1. Alpha 1 is estimated using some method, and this is an exam question, let me tell you. And if you write 26 here, you will get 25. x25 is given here. Okay, plus future error. Okay, because t is 26, we are at 25, future error will take 0. This is part of Box-Jenkins methodology. Then 0.17, we need et minus 1. Et minus 1 is e25, that is given here, minus 1.98. This is exam question. Okay, you have to put, you have to find this one. You get this, that's all. For this, okay, this is the estimated for this one, this is the estimated for this one. Okay, now when you write x27 here, for x27 also 2 step ahead forecast. Okay, you know this, you know 27. If you write, you will get 25 here, right? So I wrote 25 and 26 here. You have to write 24 here. 27 means 26 here. Okay, 26 here. So you don't have x26. Okay, but here you don't have x26, but you must have, that means to forecast for this one, you must forecast first this one. Because we don't have this one will be used. This, whatever you must have forecast here at this point, like x26 value, this is not the exact value, right? We were forecasting for this one, this value you can take here, because we don't have this value. Okay, and this will be according to t, so e27, that will be 0, and 0.17 you have to write t minus 1. T is 27 here, so e26. Okay, e26 cap, and that way you will be able to find x27. Once you know these two, then okay, this I mean I have to discuss separately. Okay, this is not a part of the course. So in one case you have both residuals given and the data is given. In the other case you have to get from your prediction. Once you predict, you have to get this residual and this data value, x26 value. These values you have to find from your prediction only, and you have to do this. See, 1 2 3 4, quite easy. I think it was a 12 mark question. Okay, the fifth part we have to discuss. Okay.